as well in the sheets here. Hello. Typically, if I have an amplifier, I will have the signal, okay, and in addition to the signal source بيكون عنده RS. بيكون عندنا الانبوت we have it at the end of the signal يعني it's between this node and the ground, and the output is always across the load. Okay, so this would be my amplifier block. We can model this as the source اللي هو VS and RS. An amplifier, it will have a gain block A, and the load which we model it typically by the effective RL. So Xn feeds X out, and XO is equal to A times Xn is a voltage amplifier, or for a current quantity IO equal A times II. For stabilization purposes, for stability purposes, typically we would like to obtain some feedback, and instead of the signal directly feeding Xi, and instead of Xi being equal to Ri على Ri plus Rs times Xs, we interject or we get some feedback from the output that is subtracted from the signal in order to stabilize the circuit. لأنه sometimes in some circumstances, depending on the poles and the zeros and the gain and conditions that we will study later, we may have oscillations, and to reduce those oscillations we need to weaken the input signal, and so we provide feedback via a block beta. We call it the beta block, where XF is equal to beta times XO based on the output signal that I sense. I provide feedback which I subtract from the signal to provide the input. يعني we will have XI is equal to XS minus XF. Okay, which is equal to Xs minus some beta times XO. And with this feedback configuration, we are targeting for stability because we are subtracting the feedback. We call it negative feedback. Okay, so in the negative feedback configuration, if we try to define now the system, instead of the direct relation between the direct relation between Xi and XO still holds, but then the relation between XO and XS, we call it AF, or the overall gain from here to here, XO over XS is equal to AF. If we look at the different relations that we have here, XO is equal to A times XI, okay, and XS really minus XF is equal to XI. So this means that XS is equal to XI plus XF, but XF here, okay, is equal to beta XO, which is nothing but beta times A times XI، لأنه فعليا ال XO هو A ضرب XI، and the XF is really beta times XO, which is beta times A times XI. So this is beta times A times XI, so therefore I end up having XS as XI into 1 plus A beta. Okay, so now all of a sudden I have XO as a function of XI, and I have XS also as function of XI, so I can write this relation, and in this relation I will obtain that this is equal to A over 1 plus A beta. يعني إذا أخذت هاي وهاي وحطيت الريشيو بيطلع عندي A over 1 plus A beta. Therefore, the feedback reduces on the main gain of the A block by a ratio 1 plus A beta. Okay, so let us see the derivation on the slide here. So now my big system is the system in red block. It relates XS to XO, and the relation feedback هو beta ضرب XO. XI is the subtraction of XS minus feedback, will XO equal to AXI. Plugging in the mass together, we get AF equals A over 1 plus A beta. Okay, so this is the gain with feedback. There are three definitions that we want to know. A is the open loop gain because it is the gain with no feedback. Beta is a feedback factor. Typically, for us, we are always using this as a constant. يعني voltage division with no frequency response, basically beta block. The A block will be a circuit that varies with the frequency for purposes of simplicity, and the A times beta is the loop gain, okay, and the loop gain is positive for negative feedback. And now we started, I have an A block, a beta block. If I want to make sure eventually that xi equal xs minus xf, I want to make sure since xf is equal to a beta ضرب times xi, I want to make sure that this quantity is positive حتى I maintain the negative status before it here. Okay, and therefore the 1 plus a beta is typically referred to as the amount of feedback. Okay, and later we will prove when we talk about stability why we want a beta to be positive. Okay, so from another perspective, but here it is shown by definition. Great. So now if we look at the properties of the negative feedback, we said that AF equal A over 1 plus A beta. For sure, AF is less than A because A beta is positive. So I want to reduce to control the gain. And also, if A beta is much larger than 1, then AF, يعني هيدا term goes away. Therefore, AF becomes approximately 1 over beta. But in general, it is limited by 1 over beta. Okay, so it becomes much less than A, independent, but much less than A. Okay, so this is the property of negative feedback. يعني the amount of control mainly is determined through the beta block. It's still a function of A, but very much tamed by the beta block. هلا, to show that the feedback is negative, we need to have A beta positive. يعني either A and beta are positive, or A is negative and beta is negative. يعني هعطيكم simple example. If I have a common source amplifier, we know that the gain from this point to this point is minus GM RL prime. So what we have to do, either I have to find a negative beta, so this A block is negative, or I need to cascade two common source amplifiers so that the overall gain negative becomes positive, and I can have a positive beta block with them. And this here becomes minus GMRL prime. As the A block, two of them will become positive, and then I can have a simple voltage division for the beta block, and the voltage division is a positive gain. Okay, we will see examples later, but I'm just giving you some hints to this stuff. Some properties of the negative feedback is that if my circuit with fabrication has a large variability, and dA over A varies a lot, the relative change in A is large due to variability, then if we compute the derivative literally, and I have AF equal A over 1 plus A beta, if I differentiate with respect to A, this becomes, I'm not going to differentiate it, هيدي هي U prime V minus V prime U over U squared. Okay, and this will give me DAF with respect to DA. And if I have DAF as function of DA, all I do is I divide it by the expression of AF. Okay, اللي هو A over 1 plus A beta. And if we do that, we obtain this formula here, that DAF with respect to AF is 1 over 1 plus beta A times dA with respect to A. And even if this was 10%, this is a number that is smaller than 1 and A beta is positive, we may end up with 5% or even less. So that's the benefit. That's why we have it, to control the circuit and stabilize it. هلا bandwidth extension. Okay, نحن مرة once we saw that if I lose on the gain, I gain on the bandwidth. So there is a trade-off. So for all our analysis, for purposes of our analysis, we will always assume that beta is a constant, but A is a transfer function, okay, with a low frequency gain, okay, with a low frequency gain and a 3 dB frequency, and it has AM, okay, it has AM and it has omega H. And therefore now if I want to simply find the 3 dB frequency and the low frequency gain of the differential amplifier, what do? I will plug in AF اللي هي A على 1 plus A beta. Okay, I'm going to remove this, okay, and multiply here by the A expression, which is AM over 1 plus S over omega H, and also in the numerator AM over 1 plus S over omega H. Okay, the first thing that comes to mind is let me multiply 1 plus S over omega H numerator and denominator. So I will end up with AM over 1 plus S over omega H plus beta times AN, okay, على 1 plus beta times AM plus S over omega H. Now I have to divide by this factor to have things as unity, so I will end up with AM على 1 plus beta AM over 1 plus S over omega H into 1 plus beta AM. Okay, so this term here is really the low frequency gain اللي هو AF هي A على 1 plus beta A, and the other term here is really my 3 dB frequency. Okay, so the 3 dB frequency increases, the 3 dB frequency I gain on it, it becomes for the feedback amplifier the 3 dB frequency of the A block multiplied by 1 plus A beta, which is greater than 1. Okay, whereas the low frequency gain will A over 1 plus A beta. فإذا the gain is reduced by the feedback amount, but the bandwidth is extended by the feedback amount. Okay, this is important for us to know. Okay, anybody has any question? Whatever we gain for the gain, we lose for the gain, we gain for the frequency. Hello. Another property that we have here is that assuming beta equals 0 is the no feedback, okay, if previously I was able to sustain an input signal, let's say, which is 0.5 volts, 0.05 volts in amplitude, يعني if I was able to send an input up till here and the output was not distorted, but if my input exceeds this value, the output may be distorted لأنه the response of the amplifier flattens here, يعني I can only amplify in the linear region, since for a given A, okay, then for AF what is happening, okay, it's equal to A over 1 plus A beta. So it is equal to A over 1 plus 0.2 times A in this example. So the AF is smaller than A, right? As we have as we see here, we're dividing by a positive quantity, and therefore since the gain is smaller, the slope, which is the gain, becomes smaller and the linear region stretches more. Okay, so I can accommodate for more input signals, larger input signals, of course, at the expense of smaller gain. Okay, so that's another property of the feedback amplifier. يعني لما AF أصغر من A, this means that the slope here is smaller than the slope here, and therefore my linear region becomes wider. Okay, so there are 4 types of amplifiers, and we will talk about them. But the first amplifier amplifies an output voltage provides an output voltage given an input voltage. We call this a voltage amplifier or a voltage controlled voltage source. Okay, and for this voltage controlled voltage source, really, in its most ideal case or most ideal situation, I will have plus or minus Vn, and I will have a gain which is plus or minus A times Vn, and this is the output. Okay, طبعا in real life I will have a resistor Ro and I will have a resistor Rn here. هيدا الvoltage amplifier as you know it. Okay, now I can have a transconductance amplifier. And what we mean by the transconductance amplifier, it's a voltage controlled current source. يعني the output is a current لأنه transconductance is a G is equal to I over V. And the input is a voltage. Okay, so the output is a current and the input is a voltage. And for this type of amplifier, if my output is a current and the input is a voltage, I will really have Vn here, maybe with an input resistance Rn, and I will have the output is really Gn times Vn, and if anything, I will really feed this current to the load, but I will have an output resistance. Let me clear it to draw it better. So here we have Vn across Rn, and at the output we have a current source, which is Gm times Vn, and typically we will have Ro and then we will have RL, and we will measure the current IO that is being provided to the load. So هيدا this amplifier has IO over Vn. That's why we call it transconductance amplifier. Okay, now a transresistance amplifier is nothing but a current controlled voltage source. يعني الانput is a current. I have some IN measured here. Okay, and the output is a voltage. So it is some resistance يعني ضرب IN. Okay, and then it has some output resistance. And really ليش اسمه trans resistance؟ لأنه هو VO على IN. And finally we have the current controlled current source اللي هو عندي IO over IN. يعني أنا as the input I will have the input source initially feeding to RS and then feeding to RN. Okay, وهيدا جاي في IN. Okay, and then in the output I will have A times IN, and I will have output resistance, and then I will have R load. Okay, so this will be A times IN, and then I will measure I out, so this will be A times IN. Okay, we will see, and here in this resistor we measure IO is the current that is flowing in the output and the load resistor. هلا we will see the example, but this is just a flashback on what these quantities mean. This is VO على VN, This is IO over VN, this is VO over IN, and this is IO over IN. نحن, for the ideal, we will explain these, but for the real example, we will focus on this amplifier. Okay, so for the real case, we'll focus on this amplifier. So, great. So now let us look. What are they showing me here? Let me first insert a slide so we can scratch on it, which is as follows. Yeah. Okay. Okay. So if I have a signal, let me say that I have a signal. Okay, any kind of circuit. This is a voltage signal plus minus. And let us say I want to sense a voltage. What do? I connect across it. What do we call this? Voltmeter in parallel. Okay. And if I want to, so let us start to write the table here on the side. So this is if I want to have a voltage or a current, okay, and this is if I want to sense, and then if I want to mix. So if I want to sense a voltage, كيف بعلق الفولتميتر across the load على ال V out إذا هيدي plus minus V out in parallel. Now if I want to sense the current that is flowing in the load, in our load, how do I sense the current?
So we put it in series with the resistors.
Right, so if I want to sense the current, I want to put it in series. Yani I have to put, if I want to measure IO, I have to put the ammeter in series, right? Such that the current flows in it. So this is in series. Great. Now, if I want to mix a voltage, and I want to add feedback. If I want to add feedback here, let us say that I want to add the feedback to this branch. How do I add a voltage source VF? ليفوت بالكي في ال loop ويدخل الفيدباك voltage to add it or subtract it, it has to be plugged in series. طيب great. If I have now to add a current, if I have some circuit where I have some current, original circuit, and now if I want to add, this is my IS, now if I want to add IF to pour into this circuit, how do I plug it in? ليجمعوا two currents, I have to mix the current or add it in parallel. And for the currents, for two currents to add, for two current sources to add, I have to put them in parallel to feed the resistor, صح? So to mix a voltage, I mix it in series. Okay, so it has to be mixed in series. To mix a current, يعني لأبعت الفيدباك and mix it, to send the feedback and mix it, I mix it in parallel. بينما to sense a current, I sense it in parallel, and to sense a current, I sense it in series. Okay, great. This is, we're gonna refer to parallel as shunt, and we're gonna characterize the different circuits names according to this characterization here. Okay, so let us see what we have here. So we have the basic voltage amplifier. Okay, I have the basic voltage amplifier, and we're going to show it in detail. What does the feedback do? It senses at the output and it mixes at the input. right? It senses this, and we will see later in an example, to multiply it by the gain beta, and then it mixes it with the loop of Vs and Vn, and we'll prove it next. If we just want to relate this terminology, since this is VO and this is V at the input, VF, Vn, okay? So sensing a voltage means a shunt or parallel, and mixing a voltage means in series. So a voltage amplifier with a feedback configuration is referred to as a series shunt amplifier, okay? And as you will see, this is what I was saying, and focus in the final prep for the series shunt amplifier types for the real example. For the current amplifier, it is IO, IN. So I'm going to sense the current, and I'm going to mix the feedback current. Sensing a current is done in series, and mixing the current is done in parallel, so it is shunt series. And likewise, we will find that the transconductance amplifier is IO versus Vn, Vf at the input. So we're going to sense a current, this will be series, and we're going to mix a voltage, so this will be series, so this is series. And for the trans resistance amplifier, I have VO at the output, I'm going to sense it. So I will sense it in parallel, and I have I feedback to be plugged in or mixed at the input, and so it will be mixed in parallel, and hence the name shunt. Okay, هيدي لحد هلا nomenology. Okay, until now we're just talking about definitions. Anybody has any questions about the naming? Okay, then let us now jump to the case of the voltage amplifier. Let us see this circuit. So here they are showing us the series shunt feedback amplifier. Let me try to draw it from scratch, and let us take a regular voltage amplifier. So this is a regular voltage amplifier. We have here Rn. Okay, this is plus minus Vn. We have here the A VO times Vn. I'm going to call it A times Vn. And we have the RO of the amplifier. And typically, ideally, I would have my input signal RS and VS. Okay, and this signal, typically we would have connected it this way, and we would have connected the load this way, and this would have been plus minus VO. Okay, what we are doing now is we are sensing the output. So we are taking a parallel connection, okay, and this sensed output, and let me draw it behind it so it does not interfere with it, and this sensed output, we are really sending it to a feedback block. So this is a plus minus VO here, okay, and this feedback block, which is another type of amplifier, which is the beta block, is going to generate a gain, okay, and this gain, which is plus minus, is beta times VO, and this will create a plus minus VF feedback voltage, okay. Until now, all I did is I sensed the output and I created a voltage equal to beta times VO. Now, if we look at this original block here, the original block, it used to be that if I assume Rn is very large, okay, and it is ideal, okay, then if Rn is very large, then Vn is approximately equal to Vs, if this is almost infinite, right? And so the loop only had minus Vs plus Rs times II plus Vn equal to 0. So Vs was really, Vn was almost, if II is very small, equal to Vs. Now, what we're going to do is we are going to break here the loop or the connection, okay? And we're going to make room, pardon me, and we're going to make room for VF to be plugged into the loop, okay? And it will be plugged into the loop in a way that it gets subtracted, okay? So here now I have all of a sudden plus minus VF, okay, such that VS is Vn plus VF. Okay, if you look at the loop, now Vs is equal to Rs times II plus Vn plus Vf. Okay, so we forced Vf into the upper block. Okay, يعني as if we subtracted VF from VS to obtain Vn. ليش؟ لأنه صار عندنا VS minus VF is equal, assuming I is very small, plus V. Okay? Clear? Anybody has any questions? Hello. We are not going always to look at it this way, but I'm just giving you the concept so that as we derive and start to use the formulas, you will be able to envision what's happening. But anybody has any question about this? Okay. So I'm going to clear this now and go back to the block. Okay, here we do not have any RS. In the ideal situation, okay, originally I had no RS, يعني Vn was equal to Vs if I remove this connection, okay, and the beta block has no Rn, and Rn infinity, and has no Ro, okay, so there is really no overhead on the load. يعني when I sense using the beta, I'm not loading the load at all, R infinity. And when I'm plugging it in, literally I'm getting minus Vs plus Vn plus Vf equal to 0. يعني Vn is equal to Vs minus Vf is equal to Vs minus Vf. Okay, so these are satisfied perfectly. And now we're going to say, well, now this is my big amplifier that wants to relate VO to VS. Let me solve for AF. هلا, what we will find is that we will find that AF is A over 1 plus A beta. Okay, and we will try also to find what is, for this big amplifier, the input resistance. We will call it RIF, and the output resistance, we will call it ROF. Yani we are starting to build recipes that we will use, and later now RIF. Why is RIF important for me? Because it is the load for a previous stage, a regular stage that has no feedback. And ROF is important for me because it tells me how much will go to the load and stuff like that. Okay, so therefore, just like we studied the Rn, Ro, and A for a regular block, for this amplifier, we're going to name them AF, RIF, and ROF. And we're going to derive their quantities as function of A, beta, okay, Rn for A, and RO for A. هدول هن للA block. Okay, هيدي Rn للA block. I have the A block has an input resistance. Here it has an output resistance. Okay, those quantities along with the A and beta, okay, are going to determine AF, RIF, and ROF. Okay, so this is very important. Okay, so let us see how we're going to do that in the coming slide. Okay, so this is the circuit again. We have it here. Okay, and now we're going to try to study the gain quantity for the amplifier. Okay, great. Let us inspect the circuit. We can go up to the bigger picture here. So let us inspect this circuit. We know clearly, since there is no load, no R load here in this image, I know that VO is equal to AVN, right? I know that VF is literally nothing but beta times VO. Okay, and from this loop here, I know that Vs minus Vs plus Vn plus Vf equal to 0. Okay, so this means that Vs is equal to Vn plus Vf, which is Vn plus beta dar Vo, which is beta times A times Vn. Okay, so therefore we can derive the gain AF, which is VO over VS method, just like we derived it for the X, as AVI over VI plus A beta times VI, so AF becomes equal to A over 1 plus A beta. So exactly what we derived for XI and XO holds for this voltage amplifier. Okay? Anybody has any question about this? So, let us now derive the quantity which is Rn. Okay. Now, since this is my amplifier, my RIF is really Vs over In, not Vn over In, because now my Vs is the new input to the full big amplifier. Okay, so it is equal to Vs over In. Type. Great. What is Vs as function of Vn? We just said it is Vn plus A beta times Vn, right? Over In. So this is really equal to Vn over In into 1 plus A beta. But what is Vn over Rn? It is Rn into 1 plus A beta. Okay, so therefore RIF is Rn into 1 plus A beta. Okay, and if you notice, I will notice this trend holds since this is series, we multiply. And this is good for us since the total input resistance has increased. نحن بهمنا ال Rn to tend to infinity in a voltage amplifier, so this is good for us. Okay, so RIF equal Rn into 1 plus A beta. This is good. Now we know the effective input resistance for this big amplifier. Anybody has any questions? Right, great. So let us now derive the output resistance. If I want to plug in a voltage source Vx here, and I want to measure the Ix here, I'm going to set the signal to be equal to what? To 0. Okay, I set my signal to be equal to 0. This means that now in this loop here, what do I have? I have Vn plus Vf equal to 0. يعني I have Vn equals to minus Vf. Okay, great. But what is Vf in terms of the output? Let us see. Here I have Vx, and here this is really Vx, and this is beta times Vx, right? So therefore Vn is equal to minus beta times Vx. Okay, minus beta times Vx. This means that in this loop that I have here, this is nothing but, so SAR A Vn is equal to minus beta A times Vx. Okay, and now all of a sudden, where is Ix here? I don't have any current, it's open circuit. Okay, so now I have a circuit that looks like this. I have Vx, okay, I have Ro, and I have here minus A beta times Vx. And this is Ix. Okay, this is my new block here. Okay, so I can now say Vx minus A beta Vx, يعني plus A beta times Vx, okay, over Ro is equal to Ix. Therefore, Vx into 1 plus A beta, I will bring Ix here, is equal to Ro. Therefore, Vx over Ix, which is the ROF, is equal to Ro over 1 plus A beta. Okay, we will see it more clearly on the second slide. يعني نحن what did we do? We shorted the input. We found the relation between Vn and beta Vx. We plugged it in on this side and we just say Vx minus A beta Vx over Ro equal Ix. And from there we found this relation. Okay, from here we found this relation that Vx over Ix is equal to Ro over 1 plus A beta. Great. So if we now look here, okay, now we have established the three definitions. AF is equal to VO over Vs, which is A over 1 plus A beta. The input resistance is Rn for the A block into 1 plus A beta, and the output resistance ROF هيدا RIF. انتبهوا RN هي للA block, RO is for the A block, so it's function of RO over 1 plus A beta. هلا something that will be common to all the amplifiers, anytime you see a series relation, you multiply by 1 plus A beta. Anytime you see a shunt relation, you divide by 1 plus A beta. And this is good for us in a voltage amplifier since the ROF is smaller than RO. This means now most of the gain will go to the load. لأن نحن بهمنا ال RO أو ال ROF تكون small, to be small. Okay? طيب, anybody has any questions? Okay? طيب, great. So let us now look at the other configurations. Since we've established this relation here, let us look at the other configuration. Now they will show me the other types of ideal amplifiers. Let us first focus on this block in yellow here. This is the A block. He's talking about a transconductance amplifier. So my A block is really has an input voltage. The A block will have an input voltage is voltage and the output will be current. Okay, hence the gain is ampere per volts. Okay, for the A block. The beta block is going, so you can see this is Vn, A, Vn, and Ro. The beta block is really sensing the current in series. So it is sensing the current. This is why it's series. And then it is multiplying it by beta. Okay, لاحظوا هون هيدا short to sense the current without loading the circuit لأنه a short does not load the circuit. And I am feeding it back in series. هيدا loop, it looks like the loop of the voltage gain. Okay, so what matters is I sense the current in series. Had there been a load, we would have put our load. Here they put an ideal load. The ideal load for a current source is a short circuit لأنه it will absorb all the current. Okay, is هيدا هو short. What is the current that I'm going to sense in this here? All the current will go to the short. So really, this whole current is going to flow here. Okay, so the IO is equal to A times Vn. Okay, all the current, no current will flow in the output resistor. So according to this, since IO will be equal to A times Vn, and then Vf is equal to beta times IO, the same will hold, the same relation will hold, and we will end up with a gain AF, which is equal to A over 1 plus A beta. We are not responsible for deriving what the RIF and ROF equals. We can directly plug them in. هلا look here that since it is a series, okay, the RIF for the full amplifier, okay, is equal to RI of the A block times 1 plus A beta, and the ROF for the full amplifier is equal to RO into 1 plus A beta. Okay, when we use them in examples, it will become clearer. But now what matters, and let us notice one thing, A times beta is unitless. Then ampere per volt times volts per ampere, so it is unitless. Okay? So now let us examine the other types of amplifier. The other type of amplifier is the trans resistance, meaning it is VO over IN. Okay, so it is VO over IN. So the A block will have similar units, and A block is the main one. It is volts per amps or ohms. The beta block will be opposite to it. It is amperes per volts. Okay, so what I do, since it's a trans resistance, I sense the output voltage. So VO is A times IN. I sense it. Okay. And then I send feedback current to be mixed with the input current source. So IF is equal to beta times VO. Okay, and this IF is then added or subtracted such that IS is equal to IF plus IN. ليش؟ لأنه this branch هيدا IS is equal to IF plus IN. Okay, by virtue of this relation, XS equal XF plus XN, and XF equal beta XO, and XO is equal to AXN, we obtain the same relation for AF if we do the math. Now the relations are shunt. I'm mixing the current in parallel, and I'm sensing the voltage in parallel at the output, and therefore what will happen, since it is shunt at the input resistance RIF will be RI over 1 plus beta A, and the output resistance, since I'm also sensing in shunt, will be ROF equal RO over 1 plus beta A. RO and RI are both the quantities corresponding to the A block. Okay, so these are the quantities corresponding to the A block. Okay, so the last configuration that we look at is the shunt series configuration. And for the shunt series feedback, it is a current amplifier. So the quantities that I am dealing with, I have a current at the input, okay, and I have a current at the output. And so my current signal is going to feed an A block, which is a current amplifier. Okay, so the units of A is amps per amps. The unit of B is beta is amp per amp. Again, my output current, since I have an ideal load, is going to be equal to A times II. And my feedback current here is equal to beta times IO. And my current IS is equal to IF plus II. So IS is equal to IF plus II. The same relation holds, therefore, the overall feedback, which is IO over IS, is equal to A over 1 plus A beta. Note that I am sensing a current, so I sense it in series. And I am mixing a current, so I mix it in parallel. Okay. At the input, the RIF, لأن عندي shunt relation is RI over 1 plus A beta, and at the output, since I have a series relation, the ROF is equal to RO into 1 plus A beta. Okay, but one last minute and we will stop the lecture. The beta block is always assumed to be ideal, يعني it is not affecting IO, it is not loading it, it is a short. And it is also not adding any resistance to the input block. There is no RO, لا series ولا parallel for the ideal case. Okay, so we will stop here and